I guess, if you'd go ahead and start.
Okay. This is Clark Morrison with the North Carolina Department of Transportation, and I'm also the chair of the Pavement ME Design Task Force. Welcome to the third webinar in this year's series on back calculation tool enhancements. I should point out Hari Nair is the co-chair of the task force. Our presenters today will be Harold von Quintus, Wouter Brink, and Yan Bin Zhang. Also, please note the presentation will be available for viewing on the ME Design resource website that is shown here. And this is a list of the members of the Pavement ME Task Force. This is the group that provides guidance and oversight for development and support of the Pavement ME software. A few housekeeping items: your phones or other audio devices are being muted. So please post your questions in the Q&A box. This can be accessed by clicking on the WebEx Q&A button. The presenters will answer all questions at the end of the webinar, and probably some of them will be addressed on the fly during the webinar. But whatever's left and whatever additional questions come up will be answered afterwards as time permits. If we don't get to all the questions, they will be answered on they will be answered, and the questions and the answers will also be posted to the Pavement ME Design website. So I think I'll turn it over to Harold and Wouter now.
Wouter, would you go ahead and thank you, Clark, very much. Wouter, would you go ahead and post the first 3 poll questions?
Yes, Harold, sorry. There was a message that popped up that prevented me from clicking the button. Okay, the poll should be open.
Right, you're given about 2 minutes to answer the poll. If those participating, if they would answer all the first 3 questions. And I think, Wouter, you're giving them about 2 minutes to answer the first 3 questions.
Yeah, and once I basically see that most I've answered, I can stop it early too.
Okay.
Okay, just a couple more seconds. Okay, it'll close in about 15 seconds.
Okay.
All right, should be good.
Okay. So we'll go ahead then and continue. You're done with the poll and everything then, Vooter?
Yes, Harold.
Okay. Thank you very much. I guess I'd like to remind everyone that this webinar, like all other AASHTO webinars, is being recorded, just so everyone notes that. And the recording will also be available on the website that Clark Morrison noted earlier. Also, before we get started, as probably most of you know, we had a lot of bad weather here in Texas, is where I'm located, last week. And my internet connection, the wireless and internet connection, having a little problem after started this past weekend. So Vooter is on standby, and for some reason my connection gets lost or I get dropped off, then Vooter's going to pick off where I left. Hopefully that will not happen. I'd also, before we like to get started, is Yanben and Vooter will assist in answering any questions that are going to be maybe asked in the chat room or in the question box. And they'll be also available to participate in answering any questions toward the end of our webinar. So with that, this is, as Clark Morrison said, this is the webinar for the back calculation tool enhancements that have been made. This is the first enhancement or first improvement of the software. We did have a lot of, after the software was released, version 1.0, in terms of the back calculation tool. We had a lot of suggestions. Most of those suggestions have been implemented. And this version of the software includes most of the enhancements, improvements that the task force approved. So with this webinar, we're hoping that most of the participants that are reviewing it do have some experience with FWD deflection basin testing, in general, back calculation of elastic layer moduli, because we're not going through kind of the introduction of deflection basin testing nor doing back calculation. We will be using the back calculation software tool, the BCT, in this webinar. Hopefully at least some of the participants have been using the software, and this is to present the enhancements that were made from version 1.0. So what we hope the participants get out of this webinar is ability to use the layer thickness segmentation process that was added to the BCT tool. That was one of the most requested enhancements, and I would look at it as being the most important. We also determine pavement structure simulation used in the back calculation, and then evaluating the results from the back calculation process using the BCT tool for use in rehabilitation. The one thing I would like to mention is the next webinar, the fourth webinar for this fiscal year, will be in using basically the results from the back calculation process for a pavement structure where you have multiple overlays in place and you're doing a rehabilitation design. So our next webinar will basically feed upon the results of this webinar. So this is the 4 items that the webinar will be include. We will do the introduction. Most of the webinar will be on the demonstration. We're going to have a live demonstration. Hopefully, we'll have a live demonstration. We will have then summary and closing comments, and then, as always, we'll have our question and answer period at the end. So, starting with the introduction of the BCT, this is a listing of the 9 important enhancements that were made. These are included in version 1.06, which is available. We're going to go through each of these 9, and in addition, some additional ones that are mainly for the users in terms of display screens and that type of information. But we'll go through each of these 9s on a typical example for doing the back calculation. The one thing additional item I would like to mention or call your attention to is that we do have some additional items and features that are being added to the BCT, and those will be available in version 1.1, which will be available in a couple of weeks to the users. So version 1.06 is currently available, and 1.1, which will include a few more enhancements or improvements, will be available shortly. U-Access, this isn't anything that has changed. Those that have downloaded the BCT in previous years, the same process is used. There is no difference there. We included these screenshots just kind of as a reminder, and where you can download the BCT with an active license. This is the specific screen where the software is downloaded. As I mentioned, there is really no change in how you access and get the back calculation tool. There is also information that was previous versions with the initial version that have to do with the EverCalc program. EverCalc is still the main engine on the back calculation tool, and we'd like to again give thanks to the Washington DOT that allowed AASHTOWare to use EverCalc as part of the Pavement ME tools that can be used. Personally, I think EverCalc was an excellent tool, and it's more production oriented, and that's one of the main reasons why it was requested for use regarding rehabilitation design and pavement analysis in accordance with the Pavement ME design software as a support tool. So you access it in the same way. We do have users, really quite a few users that have been using it, which we think is a good thing. So moving forward now, in terms of the initial screen, once you have it, before we get into the demonstration, I wanted to go over the guided process, and that's what's shown on the lower left-hand side of the screen. That guided process remains the same in the version 1.06 as well as version 1.1. The only thing that has changed, those that have used the BCT in the past, there used to be 2 other screens related to segmentation. One was defined as preliminary, another one was defined as statistical segmentation. Those are now all included or embedded under one screen which is titled Final Segmentation. And we will get into that shortly. So those two screens are now all combined into the final segmentation screen. So with that, what I'd like to do now is get into an actual demo and go through an actual problem using the enhancements that were made, or to demonstrate the enhancements that were made to the software. So I'm going to bring the software up in terms of the main screen. And I guess, Wouter, what I'd like before I get into that, you can see the screen adequately. Is that correct?
Yeah, it looks okay on my end.
Okay, great. Just wanted to verify that. Okay, so same screen that has always been there. The only additional item was the thickness data file. Now users have the ability to enter layer thickness data, which we'll get into. We'll upload a file and then go into the details of it. There is a thickness file template on the website. It's a very simplistic template, and it's just a .csv file that is compatible with importing thickness data into the VCT. The other item that is an enhancement has to do with the different data file types. All of them are the same, but we've added one additional one called the .mdb file. It's one of the newer files related to the Dynatest that many states are starting to use. So that standardized file format is now one of the 7 that can be used with the BCT. And so our example will include this .mdb file itself. So I'm going to kind of upload one of the .mdb files as an example. And this is an actual project that was done. And so I'm going to upload that. And you can see that basically just about everything remains the same on the file. Before I get into the thickness files, we still have to go through, kind of as a reminder, that once you have for each of your test points that have to do with different drop heights, we have to, or we should enter the target load. That hasn't changed. So in real time, I'm going to add the 4 target loads that was used for this example. And once they're done for one station, those target loads are applicable to any stations. The other thing that I'm going to do is, and the reason I'm going to do this for the example, 2 reasons. One, this original file did not have pavement temperatures. One of the enhancements that was added at the request of multiple users was to be able to use a standardized temperature and normalize the deflections to the standardized temperature so that all back calculation values are consistent to one temperature. Since this did not have any temperatures, I'm going to go ahead and for about 12 of these sites, I'm going to enter in 80 degrees pavement temperatures, which is between the air temperature and the surface temperature. Another enhancement that has yet to be added will be considered into the future because we think it's fairly important, but it's going to take a little bit more work than what was available for this set of enhancements, and that's using the Bell's curve. That if pavement temperatures are not entered, then that you would be able to use the Bell's curve to actually have these calculated. That doesn't exist now, but we hope that it will be one of the enhancements shortly down the road. Anyway, these I just entered on 12 of the test points, 80 degrees Fahrenheit. Now what I'm going to do is enter the thickness file. And so the thickness file is the same way. I have this, what I'm calling ground penetrating radar. The very important item, and I think in my opinion, this is a key item that will benefit many state agencies as well as consultants, because a lot of agencies, consultants are getting confident in the GPR and its use. I am also one of those individuals. And so using GPR data where you're measuring layer thicknesses along a route now can be considered in the BCT tool. The one item I want to make sure everyone understands is the BCT does not do the analysis of the GPR data to determine layer thickness. That has to be done separate from the BCT or independent or external to the BCT. Once the thicknesses are available, they can be incorporated in that thickness template. And then from that analysis of the GPR data externally, then they can be uploaded to the BCT. And so that gives us, or gives the user, the pavement designer, a lot of information on layer thickness within the rehabilitation project. And I'll come back to that on a couple of other screens because I think it's very important. There are two other items and features that I would like to note that have been added as enhancements to this initial screen. And they're shown in the center of the screen. One is called sensor settings, and the other is load sensor settings. The reason these were added, there are FWD machines like the Jill's device and or users that do not typically record sensor spacings within the FWD data file. And rather than enter those every time you use the program or every time you come back to input FWD data, then for the same type of machine where the sensor spacing does not change and for the specific data set, we can do a save sensor spacings that have been entered. If the user has to enter them manually, then they only have to do it once. They then do save sensor spacings, says okay, and then you can see that it automatically comes up in a file that says sensor spacing for this project. Those are available, then become available. And then we'll come back. And if you are using those same sensor spacings by reanalyzing your data, you can simply click load sensor spacings, and then those sensor spacings would be loaded automatically, and you don't have to type them in every time manually. So we think that that was another user request because they were having to enter these manually every time they restart a project. And so that's the reason the save sensor spacing and load sensor spacing feature or buttons were added. Again, more for a production basis for using the software. So Okay. So we've basically went through each of the different screens and added features initially. So I'm going to do a save and proceed and go to the next screen. Okay, this is now the sensor segmentation sensor screen, the second one. Again, this screen is identical to the previous version with one exception. And as you will note on the bottom, there is a thickness display screen that shows the layer thickness, wherever in the thickness file along the segment of the roadway where the deflections were measured. And so this works the same way. I can go in and click and turn layer 3, layer 2 off and just look at layer 1. I can look at layer 2 by itself or have all three. Regardless whether 1, 2, or 3 of these are checked, whichever one is checked will go to the next screen for visualizing the segmentation process. However, if the user only has 1 checked and not all 3, this 1 will appear on the final of the next screen, but all 3 layer thicknesses will be automatically populated for each segment that the user selects. And so I'm only going to leave layer 1 checked. So we have the asphalt concrete layer thicknesses as measured by or determined by the ground penetrating radar data along here. The one thing I will mention is that the limits of the GPR for thicknesses as shown on the bottom screen or display chart do not necessarily need to match the same beginning and end points for the deflection data. And what the program or what the BCT will use, it'll show whatever is the lower boundary start station and upper boundary or the ending station for both a deflection as well as however the layer thicknesses were measured. If there are borings are used to define layer thickness and you only have, let's say, maybe 20 borings along this location, then if those 20 thicknesses from the 20 borings are entered with the thickness file, then only those 20 borings will appear along the layer thickness display chart. Okay, excuse me. So what I'm going to show here is I'm just going to go through as a reminder for the basin characterization. That is showing whatever is typical versus type 2. You can see type 2, those deflection basins that are considered type 2, they're still in a conformance with elastic layer theory. And then we have what's typical, which is directly related to elastic layer theory. And for this project, you can see that we have a higher percentage of test points that are typical or type 2. Those are the ones that are generally a little bit more difficult to back calculate. I'm also going to remind everyone we can change the sensors to be used with the segmentation process. I always use the first sensor 0 for one of them, and then the last sensor, whichever is furthest from the load. And then my intermediate sensor, my preference to start is to use the sensor associated with the distance that would be around the thickness of the pavement structure. And I think we have about 10 inches into the base, so I'm going to select 12 inches here. But this only has to do with the segmentation shown on the next screen. And then I'm going to go, like I said earlier, and I'm only going to use layer 1. And then I'm going to go save and proceed to go to the final segmentation screen. Sometimes, as a reminder, if you have a lot of data, like with GPR, there'll be a little delay in moving from screen to screen because there's a lot more data, a lot more lines of data with using GPR. And we also do have quite a few deflection points within this segment of roadway. So the more data points you have, you'll notice a little bit, it may be half of a second to maybe a second kind of delay. We're not talking about anything significant, but it will not be immediate, and you'll notice just a slight delay. So this is the final segmentation screen, and it works also identical to the previous versions. The one thing I'd like to point out is, remember when I said earlier that the preliminary segmentation and the statistical segmentation are now displayed on the final segmentation screen. So the user can click on each one related to the deflection data, and whether it's the segments or preliminary, which is based on the area method. It's the area, the 1993 AASHTO Design Guide method, or simply the statistical method that is explained in the user manual, and looking at whether one segment is statistically different than the other segments with the moving average of the number of deflection points. That's the second. The user then decides what bases the user is going to have or use. What I'm going to do, I'm going to use this one here as an example, because the reason for selecting this, I'm going to come back to the pavement temperatures that I referred to at the beginning, where I entered 80 and then left NA, or not applicable, because those temperatures were not available in the FWD data input screen. And this will have to do with the temperature adjustment that I'll refer to in the latter part of the demonstration. So I'm just going to have two segments. You can see that these two segments, just like they did previously, they come up with segment 1 and segment 2. All of that is identical to the previous version. What is different, or what was added, if you note at the bottom right-hand side of our screen, you now see layers 1, 2, 3, and 4. And that's because there were 4 layers that were included in the thickness file that was imported into the BCT. And so what we have to do now is we have to assign the generic layer definitions for each of these layers. For this project, the first layer is an asphalt concrete surface. Layer 2 is it's really a stabilized aggregate base. It's a lime kind of fly ash stabilized base. The third layer then was a coarse grained subgrade, or an embankment material that was placed during construction. It's an embankment, but coarse grain. And then the subgrade is a fine grain type soil. What I'd like to mention here is that this layer of structure entered is for the entire, what was ever in the data, the layer thickness file. and that's assigned to the entire deflection, the length of the deflection basins. We all know, though, as we go through a project, along a project, we can note some differences. And so I'll go through how this layer structure can be revised when we get to the structure definition simulation or the next screen. But the important point that what I wanted to mention is that what you see in terms of number of layers and how you assign those should be typical for the majority of the pavement site as we go through from one end of the project to the other end of the project with the deflection data. But that's just on the overall project. When we get into the actual structure segmentation, we can manually override any specific area and or specific segment that we would like. Okay, so then I think I've mentioned everything I wanted to mention on this slide. So I'm going to then save and proceed. And now I'm into the pavement structure simulation or the structure definition simulation screen. This screen is the same, but there are added features that have been added. So we have two segments shown by the boundaries between segment 1 and 2. So I left click on the segment 1 or within segment 1, just like we did on previous versions. So this comes up and we have the pavement structure, the average layer thicknesses, and the different layers, layer 1, 2, 3, 4, with the average thicknesses for layer 1, 2, 3, 4, that come from the layer thickness file within these boundaries. So these thicknesses represent the average thicknesses from the layer thickness file that the user defined for the boundary conditions or the segment boundary conditions. And so this will be 4. I'm going to leave these 4 layers as I defined them for within the final segmentation screen. So right now I'm not going to change anything on this screen, and I'm going to go to apply. And now you notice that turns green because I just accepted it. Now what I'm going to do is I left clicked on the other part. These now are the layer structure that came up, the different layers and the average thicknesses for each of these layers for this segment between the start of this segment and the ending station location for this segment. The one thing I'm going to do, though, I'm going to change layer 2, and this is 10.24. Going to change the layer and say now this is an aggregate base that has not been stabilized. And so I'm going to click on that. And the one thing we still have to then enter this 10.24 inches because we're changing the material type from what we originally defined under the final segmentation screen. So I'm going to then leave these as is. I'm going to go back and just make sure, that the first segment is the same. And I'm not doing anything with the minimum or maximum, but the information that is included in the user's guide for setting the minimum and the maximum apply always. And so as a reminder, the BCT tool sets the minimum and maximum, assuming these were good in-place materials. For example, it assumes that you do not have any major cracking in the asphalt layer. You wouldn't have any stripping in the asphalt layer. It assumes a good, or for concrete, you know, an intact material without uncracked slabs. And we all know that we can have cracked slabs, we can have stripping, we can have fatigue, bottom-up fatigue cracking in the asphalt. So the user is encouraged to always look at the min and max values and ensure that we're not going to hit the boundary conditions for whatever reason, either the lower or upper boundary conditions or modulus values when we do the back calculation. So I'm going to leave these as is for now. And the other feature that we see on this screen is a stiff layer. Right now, I do not have it checked, and I'm going to go through this first demo without the stiff layer. Then I'm going to come back after we've done that, and I'm going to then click. Well, let me do that now to show how that will happen, because in our initial borings, which were anywhere from 5 to 10 feet, there was no stiff layer, so we do not have any stiff layer. But from other data and information from this site, we know that there are very hard layers down below, or typically down below. The depth just is significant, can vary significantly. So even though we didn't see it in our borings and we know that there may be, I'm going to go ahead and click. It does have a stiff layer. And for that, now I'm going to use 5 layers because we had 4 measured. So if I click 5, now you can see here's our layers that appeared from the data thickness file. And what I'm going to say, this is our bedrock. And 0 means it's infinity or infinite. Now I'm going to come in. This is our fine graded soil at the bottom of the borings, or the lower part of the borings. And I'm going to estimate that that's 120 feet. It's beyond the deepest depth of our boring that were done for this project. And those borings were basically to confirm the GPR results. So now we have our subgrade. I'm going to leave these as is. Everything else, I believe, I'm going to have a stiff asphalt layer, which is entered. So everything is applicable. So I'm going to hit apply. And then I'm going to hit save and proceed. This screen now comes up. We're on the back calculation screen. And that back calculation screen is the same, with the exception we have one added feature. And this is the temperature correction that you can see in the center part of our screen here. I'm not going to turn these on yet, but this feature allows a temperature correction for those users that want to correct their back calculation modules or do the back calculation to a standard temperature, let's say 68 degrees or room temperature, because that's what they have for their other data. The BCT now allows that to happen. I'm going to turn it off though. So we're not going to back calculate. We're still going to back calculate at whatever temperature was in the FWT input file. So my the sensor locations, and I'm just going to hit now back calculate. And now it's going to go through its back calculation. So for all of that, using the average layer thicknesses for those 2 segments, it's complete. I'm going to hit OK. And now I'm going to go to the segment selection. I'm going to look at the results for that first segment. If I click on that, this shows me the layer thicknesses display chart as a function of distance. And this shows me, the lower chart shows me the root mean squared error for each of those points as a function of distance down the road. I'm going to turn on the logarithmic scale, and then I'm just going to quickly only look at the AC first. And you can see where that's for the asphalt. I can then look at the treated base. You can see it, that's probably treated because it's well above 100 KSI. And then for each of those points, then I'm going to look at the coarse grains subgrade, the embankment, which has a very high modulus. And then I'm going to look at the subgrade modulus within that segment. The root mean squared error screen or chart display shows we have 1 point that's above 5% for this segment. So I'm going to look at the other segment now. And I'm going to do basically the same thing. You can see we have a couple of points that have very high root mean squared errors. I would not have confidence in those points. I'm now going to look at the same thing I did previously. Here's our asphalt concrete layer modulus. Here's the granular base, and you can see we're hitting the boundary conditions. We're assuming this was not stabilized, and we're hitting the upper boundary. That could be the reason for some of these higher root mean squared errors. Going to the subgrade coarse grained, and then to the lower subgrade layer, and then finally the bedrock layer. So the first thing I'd like to do is with this, look at now the layer compensation. And this is exactly the same that was in previous version. For our first segment, there was only a subgrade, coarse grain, subgrade, fine grain. You can see the R squared, the slope is positive. There's really not a good relationship. So remember, we're looking for highly related layers, that unbound layers that are inversely proportional, because that's a sign that we're in an area where the increase of one layer is simply reducing the other layer modulus, and they're being inversely proportional, which typically doesn't happen in the field. This is the other segment, and remember here, this is now the base and the subgrade. They're not related, but again, on the granular base, we're hitting the boundary condition. So I'm going to look at now the two subgrade layers, and again, they're not related, but we're hitting the boundary condition. So I'm just going to say, oh, and then the depth of bedrock. This is the other item that was included, our depth to bedrock. And we had the depth to bedrock in the second segment. And now this shows, since we had that check, this is the tab to look at the depth to bedrock and how that varies along that segment. And you can see that it's very deep. I initially assumed 120 inches, and just about all the values are much greater than that. So in actuality, we could simulate, or probably should simulate, this segment as an area without bedrock. And so what I'm going to do now, I'm going to go back to here. And what I want to do is look at the modulus values and then come back with a temperature correction and look at those same values. So I want to save and proceed this section, but before I do that, I'm going to enter like 5%. it's the maximum the user manual suggests the user enters, and then kind of hit an update, and then it removes those data points where the root mean squared was greater than 5%. And then I'll hit save and proceed. The physical feature screen really hasn't changed. It's all the same. This data file did not have any transverse cracks, load transfer data. So we don't really have load transfer efficiencies being measured with the deflection data. Basically, it gets entered the same way. The numerator would be the whatever deflection is on the other side of the crack, and the denominator is where the load plate is on the opposite side of the crack from this other, or however the agency is using the deflection basins to measure deflection or to measure load transfer efficiency. As I noted, this deflection, load transfer efficiencies does not exist in this deflection data file. So it's not going to be used. So, and then this shows the different drops. So I'm just going to leave it as is. And I'll hit save and proceed. And what I want to look at initially is this is the first one. We have about 620 KSI. The lime treated subgrade about 140. The coarse grain soil is about 73 KSI and the subgrade 42. So you can see the coefficient of variation is very low here. That indicates we had very low variation, which is a good thing. I'm now going to go to the second segment, which I changed lime treated to a granular base. And you can see we still have from segment 0 to 1, we still have, about 900 KSI for the AC. We still got a pretty high modulus for the aggregate base, pretty high for the coarse grain soil or the embankment. What's defined as an embankment, it's a coarse grain material, and then the fine grain, and then the bedrock. Again, very low coefficients of variations, which means the deflections were relatively uniform, and we probably have fairly uniform thicknesses within each of the segments. And so before I get into these files here, I'll come back to these. So what I want to do now is I want to go back to our back calculation screen. I'm going to go backwards. And I'm going to come into now what we defined as temperature correction. And I want to turn it on. And so now what we're going to do, we're going to back calculate and normalize everything back to 68 degrees. Remember, the air temperature is around 75. The surface temperature was around 85. And for the first 12 points, I entered 80 degrees as the average pavement temperature. And the pavement temperature, that would be mid-depth in the asphalt layer. And so with this, I'm just going to do back calculate. And so it's run. And so what I want to do now is I want to look at that segment where I entered the deflection data. And so now you can see we had about, I guess it was about 600. And now you can see if I turn the others off for the asphalt, now we're about over a million PSI, but that's at 68 degrees, not at somewhere around 80 degrees. Okay, and if we look now at the second segment, you can kind of see where the values that I entered for 80, they're well above a million PSI or 1,000 KSI, but at 68 degrees. Below that, or after that last point I entered, they're all NA. So the user, if the user does has a data file, an FWD data file that doesn't have pavement temperatures entered, you do not want to use this feature to normalize the temperatures because it doesn't have anything to normalize them to, because you don't have the pavement thickness temperatures entered. So with that, there will be, if we try to normalize with a file that has no temperatures entered, pavement temperatures, then there will be an error message that will be displayed that the user will not be allowed to use this feature here. Right now, since I entered 80 degrees, it did calculate, but these values at the end of the segment are not true values at all, because they're based upon the NA entry within that data file. So just remember, for all users, if you do not have pavement temperature, you will get a message coming up that that's not allowed. If you do enter pavement temperatures for some of the files right now, it's going to calculate or determine the normalized moduli to the standard temperature, whatever one you entered. But those values are inappropriate for the asphalt concrete. Okay, so what I want to do is I'm going to come back now to without using the normalized temperature screen. And so we should come back to exactly what we showed previously, about 600 to 700 KSI for the asphalt, and then the others. But now what I want to do is I want to go back to the structure definition file. And so since we have a deep, stiff layer here, a lot deeper, what I'm going to do is I'm going to turn off the stiff layer now, and I'm going to go back to only 4 layers. And now what I'm going to do is have 0. And if you remember, we were hitting the boundary. So I'm going to up this for the layer 2, which we really considered a stabilized layer. And for both of these layers, I'm going to increase the upper modulus values, and I'm going to hit apply. I'm going to go back. This one's already up to 1,000 anyway, because we defined it as a stabilized. And I'm going to hit this one as 100 like on the previous one, but I'm going to leave it at that. And then I'm going to hit apply again, and then just hit save and proceed. I'm going to leave the temperature turned off. I'm going to hit back calculate again. I'm going to hit OK. And then I want to look at, again, each to see what happened to my root mean squared error. And as you see for segment 1, I'm in segment 1, everything is about the same because we didn't simulate a depth to rigid layer. I'm then going to go to segment 2. As you can see, now we have only really one point that's above 5%. All the other layers, let me do this. Yeah, they didn't change. So all the other layer points now, with removing that rigid layer, we got a lot better fit to our measured deflection. So I'm going to remove that 1 or 2 data points that above 5%. What we got very good root mean squared error. Most of them are less than 2%. And so I'm going to go back and just look at our screens. They're basically the same. So I'm going to go back and then do save and proceed, because there's one other item I want to show the users as a feature that was added. So here's segment 1. This is an asphalt concrete, and it's still 635 KSI. at about 80 to 85 degrees Fahrenheit. This was what we called the line flash for segment 121. This is now an A1B for the coarse grained embankment. And then our subgrade was an A6 at 42 KSI. Still, coefficients of variations are very good. Here's the layer thicknesses. Go to layer 2, segment 2. This is now the asphalt concrete at 773, about the same as segment 1. Very good coefficient of variation. Granular base. What I'm going to do now, this granular base, you can see that it's not stabilized, but it has very high value. So I'm still just going to call it a crushed stone, but this lane is probably a line stabilized aggregate base also, because it's got about 144 PSI. But the coefficient variation is good. I'm going to call my embankment still an A1B, and then the subgrade as an A16, and this is all good. Very low coefficient variations. Here's my average moduli for each of the layers. So what I'm going to now briefly go through is we have these other two features that were added. The reason these were added, some agencies or some users, I should say, wanted to normalize the data to a specific to their target drop height. And so that they do not have deflections where the drop height is varying or the drop load is varying. They want to normalize it to their target load. This other button is export the BCT data so that we can look at it, and it's converted into a .cbs file to allow users to look at and easily evaluate the results from the back calculation process for each of the segments. So if I click on, let's say, normalized deflection data, and it should go to, let me do then the export, and I'll show where the normalized deflection data, hit export, and then I go to file location, and now I see the segment 1. And the segment 1, I think, yeah, the segment 1, this includes the EverCalc export. That's the file we just exported. And this also includes the normalized deflection file. And so if I open the normalized deflection file, there you can see the stations, the load levels that are now all the target load, 9,000, 12,000, 16s, and the deflection basins have all been normalized to those target loads. And so through the end of the project. So that's our deflection file. I would like to mention we have had one user, or I shouldn't say one, a couple of users now, that would like to normalize when you have different drop heights, to go ahead and normalize everything to either the target load or to a specific load level. For example, either 9,000 load pounds or 12,000. And so in the next features that will be added, the next version that comes out, this will have everything being normalized to a specific load, if that's what the user would like to see. How the program or the BCT normalize this is just like EverCalc. It's the same mathematical process in EverCalc that's used in the BCT, because EverCalc is the engine. So what I'm going to do now, I'm going to close this one, and now I want to go into the EverCalc export. And now you can see we have S1 and there is an S2 because this is segment 2. Section 1, segment 1, section 1, segment 2. And so I can first of all look at segment 1. And this now shows me what the stations are, the actual load levels, the modulus of layer 1, 2, 3, and now 4. And what's shown here is the total depth. This is the total depth of the pavement structure, and then the root mean squared error. But now the user can go through and for all the values in segment 1, prepare whatever plots, look at the data maybe differently, whatever the user would like to do as part of their rehabilitation design process. So I'm going to get out of that one and then show simply segment 2. Same thing is shown for this segment. So all of that is basically the same. So I'm going to go out and then I'm going to get back to the BCT. And the export to ME design is identical to what previously, but you can see I just made an error. The program told me I made an error because I forgot about something, the analysis type. So our analysis, we're going to use this for rehab, is asphalt over asphalt, asphalt overlay over asphalt. The other thing I want to mention is this temperature, because we had a temperature of 80 in the deflection file. So now 80 comes up. If we had NA, like we did, this would be NA or 0. And so the user would have to then populate this in the Pavement ME design file. So I'll do export. I'm going to do this for segment 1. So both of the segments are now populated. I'm going to hit go. And then it's been populated to the screen. So I can go now to that export button, and then here's my files, ME design project files, and here are my 2 segments that have all been populated. And so now this kind of concludes the demo for this webinar in terms of using the new enhancements, improved features for Pavement ME. And for the webinar 4, we're going to pick up where we left off here in terms of designing an overlay for a existing pavement structure that has multiple asphalt overlays. So with that, I'm going to go back to basically the presentation, and there are a few slides before we open it up to our question and answers. I want to go through about 2 slides, closing comments, and then the questions and answers. So, and I've really already made this comment. The enhanced BCT version was based on suggestions from the users, as well as what happens to enhancements and improvements made to the Pavement ME software. So I believe Clark Morrison mentioned this earlier, but I want to mention it that the enhancements and improvements that are made to the software come from the users. And so as you use the BCT, as you use Pavement ME, and you'd like to see things done differently or features added, please submit those to the task force and or the help desk and or AASHTOWare itself. And the task force will consider all of them and then try to put them in the tunnel for making the changes and or improvements at some point in time. It may take maybe a fiscal year or 2 fiscal years for them to be made, but they will be considered. The other is, and this has to do with adding additional suggestions also to the pavement ME, which is I've already mentioned. So with that, Vooter, I'm going to, if you would ask 3 questions, final questions, and then we'll do the poll questions, and then we'll do questions.
Sounds good. Poll 2. Looks like about 75% has responded. We'll give it about a minute, a little over a minute left. About 30 seconds. All right. 15 seconds just to close out some of the responses. Okay, the poll is closed. right, Harold, I think we're ready to go.
Okay. Question and answer. Were you able to answer most of the questions? I guess, do you want to go through those that were not answered and read them and then answer the questions?
Yeah, some of the more recent ones we didn't get to, but we try to answer most of them. Okay. First one that we weren't really able to get to is, this is from Pershwall. It is likely to have non-unique solutions of back calculation, that is, more than one combination of layer thickness and modulus will be the solution while following the back calculation procedure. How does the software BCT identify the correct solution?
That is specifically answered in the user manual and also in the manual of practice for Pavement ME regarding rehabilitation design. There's really only one program I really know of that has a unique solution, and that's LMOD. I believe it has a unique solution. Most back calculation programs do not have unique solutions. EverCalc is one of those. You can have multiple solutions, kind of which one is correct. The way I make a decision on which answer or result of back calculations that I'm going with, as well as the pavement structure simulation, has to do with the root mean squared error. I try to get the root mean squared error, the lowest value as possible. But for EverCalc and many other back calculation tools, there is no unique solution. That's a judgment of the user itself or the designer. And as I said, I use root mean squared error to make that.
Okay. All right. Next one. What if we have GeoGrid or geotextile between subgrade and base course? How can we put this input in back calculation?
The GeoGrid and geosynthetics, those are very thin layers. Obviously, on back calculation, you're not going to back calculate the stiffness of a GeoGrid or a synthetic layer. What you would have to do is what impact does that GeoGrid and or geosynthetic have on the response of the aggregate base that was within the pavement structure. That is also the same with just about every other back calculation program that I'm aware of. You're not going to back calculate a stiffness or a feature of very thin layers, very thin layers or other layers like geotextiles, geosynthetics, very thin layers that make the pavement surface for whatever reason. The back calculation structure is limited to 5 layers. And so you have to make a decision on how you're going to simulate the pavement structure using more than 5 layers, considering the last layer.
Okay. Could you please show an example of the GPR data as input? I think you had one of these in your slides, Harold.
I did.
But not in this version.
No, it is in the slides. Let me go back.
If it's easier to open the file, that's fine too. I think it's that import.
Here we go. Here's the file. And it's simply, this is the boring file, but the GPR file is identical to the same thing. Wherever your thickness is or for that station, the station, and whatever the the thicknesses are by layer from the independent or external evaluation. So the GPR file would be basically no different than this file shown here for borings. I did have, I did have a file structure, and let me see if I can find it and bring it up. Here we go. For the no, that's wrong one. I may have I'm almost sure
You
override.
said in test files 1? Yeah.
It's in here, and here we go, GPR layer thickness files. Here's the layer thickness file for GPR. And again, it's what this user, we got these files from a specific user. The user took all the GPR data, determined what the thickness is for on a per 100-foot basis. And then every thickness for the surface, the base, this base, and then the embankment layer are entered. So this is a typical GPR file. It would be very large, a lot of lines, because data is a lot of data. But again, I want to emphasize, make sure everyone understands, the BCT does not do the interpretation of the GPR data. That has to be done externally. And the thickness derived from that GPR data are then included in this thickness format that's available, template, and then those then can be entered into or imported into the pavement ME thickness file. So I want to make sure everyone understands that. Anyway, hopefully that answered the question.
Yeah, I think so. And there's also a sample file on the ME Design website under the BC back calculation tool.
Yes, there is.
Yeah. Next question is, what is your maximum recommended value for coefficient of variation?
Yeah, that's a good point. I didn't mention it. I know in the user guide covers that specifically. That's also kind of dependent upon the use. What I normally use, I try to get that coefficient of variation down below 50%, certainly down below about 75%. As the thinner layers you have, typically that coefficient of variation is going to go up. If you have a lot of variation in thickness along a project or along a segment, the coefficient of variation is going to increase and or go up. The files that we had from the GPR that I gave the example were very good. The project was built relatively uniformly, so we did not have or see through the borings and or the GPR data a lot of variation in thicknesses. It's a pretty uniform project. When you have that and you have or typical deflection basins, the characterization, you should get the coefficients of variations below 50%. If you have a lot of thickness variation along a file, or if you have other things varying along a file, well, we got thin layers, you got a lot of cracking along the project, you got other things happening, stripping along a project, you got voids under the slab along the project, coefficient variation is going to go up. And getting an elastic layer solution for a non-elastic layer problem or simulation is an issue. It's what pavement ME is based on. So I try to keep coefficient of variation in summary below 75%, typically always.
I'm just adding it to the response here.
Okay.
Okay, this one's been answered. There's a context for this question. Does the asphalt thickness have any effect on the deflection shown for a given pavement temperature entered? And to it, in addition, is temperature differential across the AC depth, presumably there is no consideration by the BCT for temperature.
Temperature is considered. It's very important, but it's considered, deflections don't affect temperature. Temperatures have an impact on deflections. We back calculate at whatever temperatures are entered in the FWD deflection file. That is one of the items that we are going to go over in webinar 4 that will have to do when we have different temperatures that are entered. We have different files created, how that temperature can be considered, and whether we have back calculated to a standardized temperature as I showed in this webinar. So if you have pavement temperatures in your deflection file, you can then enter a normalized deflection, and the BCT will calculate or produce a result that is a back calculated modulus to that temperature, that standardized temperature that the user entered. That adjustment or normalization process is exactly what is in EverCalc, the EverCalc program itself, because that is the engine of BCT. Let me go on just one additional comment. It is always my recommendation, we do not back calculate at a standardized temperature, even though I know it's done in industry and a lot of users do that. My suggestion is you back calculate at the temperatures for which the deflections were measured. And you have that in the deflection file. Then you use that in rehabilitation and allow pavement ME for the dynamic modulus master curve to correct for temperature differences, both for the existing pavement as well as for the overlay. Okay. Back to you, Victor.
Sounds good. Let's see. One question is on, can you share the results of the poll questions? We'll have to talk to AASHTOWare and Pavement Redesign to see if we can add that to the website.
Yeah, I think we should be able to do that.
Yeah. Okay, these are good. If we have longitude and latitude in the FWD data, can we use longitude and latitude in GPR data?
If you measure longitude, latitude in your GPR data, then yes, it can be used, not the reverse. So yeah, if you have the longitude, latitude, and GPR data, yes, you can use it.
Okay.
I see the other question. I'll read it. This makes sense to use FWD or LWD to get data first on unreinforced sections and after reinforced to compare the effect of the geogrid. Okay, I see that's kind of in response. So the one thing I want to mention when I saw lightweight, the LWD, using the back calculation tool, if you've got, depending on how many sensors you have, be careful about using LWD data to back calculate layer moduli unless you have multiple sensors with the LWD. I know others don't agree with that, but that's my comment. And I think we may need to get it back to how many more questions, Vuder? Because we probably, I think we're at 2:30 now or getting close. So.
Well, I think we scheduled it from 12 to 2.
Oh, well, then we're fine. Okay, I'm sorry. I'm sorry.
No, the last one was 90 minutes total, I think. And
Okay, I apologize. Keep at,
oh, yeah.
let's
I mean,
finish it.
you can see them too. The next one is, can you switch units in the software? The units is typically based on what the FWD file uses, and there's only certain types. I think the F20, Yambin answered earlier that, let me see.
Yeah, on the units, you cannot mix units in the middle of, let's say, within the run or within a problem, with the exception of distance. The program, and this is defined in the user guide, you can use metrics or English to define distance because back calculation is not based on distance. It's where the test results are made. There is a US customary version, which I used, and there you have to have US customary unit, which has to be within your FWD deflection file, a pavement thickness file. There is also an SI version, and with the SI version of the BCT, you will need to use SI units in the FWD deflection file, as well as SI units in the layer thickness file. That has to do with the deflections, temperatures, thicknesses, but what's not related to that is distance, because we're just, we're not doing back calculation. Distance is not a factor. It's only where the point is applicable to. So for distance, you can use milepost, you can use feet, you can use stations, you can use another alpha or another numeric term, whether that's SI or US customary. But let me they have to be the same between the deflection file and the thickness file. You have to use the units, regardless as SI or US customary. For distance that's in the deflection file, those same units or how we're describing distance has to be the same in the thickness file. How the thickness is, their distance, how the distance is located by borings or by GPR.
Yeah, and I also just want to add in that as a stated in the user manual, basically the tool selects the appropriate units for all variables in different modules based on the input file.
Okay.
Yeah. Okay, next one is, you mentioned thin layers often. Is 3 inches considered thin for both AC and base layers? Or is different for base and sub-base layers?
It's different. It's different depending upon the layer you're looking at, or from the surface of the pavement. The user manual goes into this. I think also the manual of practice has the stimulation rules. That's the pavement ME manual of practice. Those same type of rules are also in the back calculation tool user manual. But to answer that, I'll kind of give you what I generally do and or suggest. And that is, the deeper we get in the pavement structure, the thicker the layer structure for back calculation to get a reasonable result. If at the surface layer, I have used for the asphalt concrete as thin as 2 inches and have felt comfortable with the results. Typically, that's 3 inches, but it's going to be dependent upon the pavement structure. Typically, the minimum is 3 inches for the surface, the bound surface. Then the base layer, the layer below that, whatever it is, either a cement stabilized layer, an aggregate base layer, whatever. The layer below that is typically thicker than the wearing surface, whether that's about 1.5 times the thickness, but it generally has to be thicker. So, and then the layer below that has to be thicker than the previous layer and on down as the minimum thickness. And that's a general guide. What, in terms of the different layers, what I try to do, and the more sensors we have, the better we can do the simulation. And that is where the sensors are located. That's also related to the layer thickness. For example, if you go from and I mentioned this in webinar 3, also mentioned it in the first webinar we did on back calculation, but that's if you've got a sensor located 12 inches, let's say 8 inches, 12 inches, 18 and 24, and we've got a 6-inch asphalt and then a 6-inch aggregate base, and then below that we got something else. Sensor 1 or 2 may be kind of indicative if it's at 8 inches of the asphalt base combination, and the sensor from that, if it's at 12 inches, may indicative more of the base layer, and so down. So there's the distance that the sensors are located from the loading plate versus the thickness of the different pavement sections, or their depth below the surface, are somewhat related, and users should consider that. But the user manual goes into a little bit more detail, or let's say a little bit more text is provided, and not me being too verbose on this answer.
Yeah, and basically there in the manual, layers having a thickness less than 3 inches or 7.5 centimeters should be avoided if possible. But
Yeah.
like you mentioned, you've had success and felt comfortable with less than that. It just depends on the structure you have. Okay. Next one is, does Pavement ME use the variability of the BCT results?
Variability of the BCT is not reused by the Pavement ME software, nor the BCT. That's provided as a guide to the user to know whether you got reasonably uniform results or whether they're all over the place. If they're all over the place, the user should reconsider his simulation and or reconsider the segmentation process, or what they have defined as the different segments. But that is provided as a guide to the user on the uniformity of the results within a segment.
Okay, and looks like the last one is, do the GPR layer points for layer 1, 2, layer 1, layer 2, and layer 3 have to have the same station?
Not sure I quite understand the pavement, the question itself. GPR, okay, at a station. That's a very good question. I should have mentioned this at the beginning in the thickness file. And I don't have a good thickness file to demonstrate the difference. But let's say you have 2 segments. Segment 1, you have an asphalt layer, you have an aggregate base layer, you have a stabilized layer, and you got a soil layer in layer 4. You have 4 layers: asphalt, stabilized, aggregate base, soil. That's the project. But you got these couple of areas that you do have the asphalt, you do have the stabilized layer, but there's no aggregate base, and then you get into the soil layer. when you set up the layer structure, you should enter 4 layers either from your borings, setting up the file, or GPR, the 4 layers. But in the areas where either from the borings or the GPR data, you do not see an aggregate base. It's not seen in the GPR data, or it's not seen in the recovery of the materials from the borings, from the boring logs. Then for those areas, you would simply enter 0. And when the BCT establishes that segment for which there is no aggregate base, then there would be 0 thickness for that layer, and the user would simply delete that layer from the pavement structure. And then you have that segment that has different layers. The BCT will be able to consider the different layers along the project when the structure or the underlying layers may change, either from type or some of the layers may disappear. They may be contaminated and you just can't see them for whatever reason. But the DCP does allow the user to do that, but that decision has to be made within the thickness file. The BCT cannot make that decision. The user has to make that decision in setting up the BCT file, the thickness file, the BTC thickness file.
Okay. 2 more questions came in, Harold. Let's see. One was sent in chat, but is Pavement ME capable of converting the FWD data into dynamic modulus master curves?
The answer is no. Right now, the answer is no. Where it gets converted is in the Pavement ME. And that's the reason it was not done in the BCT.
And that was the question, Harold. It was in Pavement ME.
Oh, I'm sorry. In Pavement ME, yes. The conversion is done in Pavement ME. Yes, that is correct.
Okay. All right. Now it looks like last one. Can we say BCT should not be used for low volume roadways that has less than 2-inch AC layers, or is it generally not practical to calculate structure with thin layer AC or just seal coat?
Yeah. I'm going to give you in answering that question, I'm going to give you my experience, because where I'm from is in Texas. I don't know if any of the participants, if they're individuals from TTI or TxDOT on here, they will be very experienced in answering this question. But I'm going to give my suggestions, my experience. The answer is yes, the BCT can do that, but you have to be very careful. And you have to look at the results. You can't just automatically use the results. But yes, you can back calculate for very thin layers, either seal coats, double bituminous seal coats. We've got a lot of those in Texas. We've done back calculation on those, where the seal coat's setting on a crushed stone, that's on a lime stabilized subgrade, and on soil. And that's been done. You can do it and either have it back calculate if you've got, let's say, a very thin asphalt, 1.5 inches, or you've got a triple bituminous surface course that may be 1 inch to 1.5 inches. It's not an asphalt, but it is a bound material. Or you can simply set those as a known value. For example, you don't back calculate, you check it just like you do a bedrock, and you enter the stiffness value that you think is representative of that structure, and then the BCT will back calculate the remaining layers. So it can be done, one of 2 ways. But typically, the coefficient of variation is typically pretty high for the conditions.
Okay, it looks like one more came in. Do we need to measure moisture content of base and subgrade layers as an input to AASHTOWare Pavement ME when using back calculation results to represent the same conditions as in the field at the time of testing?
Yeah, I'm glad that was answered because, or asked, because that tells me individuals now are thinking about input compatibility with pavement ME design, which is very important. And the answer is yes, you should enter the moisture content as a minimum and the density for the unbound layers that are associated with the time at which deflection testing was done, so that you have a compatible back calculated elastic modulus with the moisture or with the physical conditions of the unbound materials that existed at the time of deflection testing. So yes, that should be done. It's not always done, but I usually suggest and recommend that it be done. At the minimum, get the moisture content. Did I get the answer the entire question, Vooter, or?
Oh, sorry, I was muted.
Okay.
Yeah, I think we're good on the question. Did you have any that were submitted to you directly in the chat box instead of the Q&A?
I have, let me check real quick. I don't. That was just the one you just asked me about the master curve. That's the only one I have in my box.
Okay, sounds good. That's the only one I had too. Okay, I think that's all the questions.
Great. We ended early.
Yeah.
Okay. What I'm going to do then is, Clark, I'm going to turn it back to you. Oh. Let me get to where we were.
Okay. Can everyone hear me now?
Yes.
Okay, so just a reminder that webinar number 4 is coming up on asphalt overlay design for pavements with multiple overlays and deflection data. And watch out for the announcement for it. It will be coming in May or June of this year. Again, thank you for attending. We had a great turnout. You have contact lists here for Ryan Fragapane with AASHTOW. My contact information is there, as well as the help desk and the ARA staff. So any questions or comments, we'd love to hear them. Also, I would remind people that the recording of this webinar, along with a transcription of the Q&A transcription of the Q&A will be posted to the ME Design website, which is shown on the screen now, www.me-design.com. So look there for the recording and the transcript. And again, thanks to everyone for attending very much.
Thank you.
Thank you, everybody.